Okay, so do we have any questions? No questions? Okay, good. So we're going to talk more about quadratic functions today, and that's section 3.3. So a quadratic function is the one of the form f of x equals ax squared plus bx plus c. And the graph of a quadratic function is always going to be a parabola. Okay? So a is not equal to 0. So the graph of such function is always going to be a parabola placed somewhere. We don't know yet. But at least we're going to know one thing. If a is positive, if the leading coefficient of your function is positive, the parabola is going to open up. And if the leading coefficient is negative, the parabola is going to open down. So that's if a is less than 0. And it's kind of going back to the transformations that we talked about last week. If you have a negative in front of the function, it flips over the x-axis, so you're ending up with an upside down parabola. Now, if you have a normal parabola that opens up, it will have a minimum point at its vertex. So that's what we call that point right there. It's a vertex of a parabola. So if your parabola opens up, it will have a minimum, right? So there's nothing below this point right here. At the same time, if the parabola opens down, the vertex of that parabola will be the maximum. So we can predict whether a quadratic function is going to have a maximum value or the minimum value depending on whether it opens up or down. Okay? And how can we determine whether a parabola opens up or down? What can tell us right away? What? Yeah, positive or negative in front of the x squared. Good. So, for example, if I just ask you whether this function has a maximum or a minimum, and I write something like this, you'll say it has a maximum, right? Because the parabola opens down to have a maximum point. So it has a maximum because the coefficient in front of the x squared is negative. Now, finding that maximum is a different story. So to find the max or minimum value of a quadratic function, we just have to find the vertex of that function. So the big thing that we're going to talk about is how to find the vertex of a parabola. Algebraically, without using the graphing calculator, because I know you all enjoyed that during the last week's homework assignment, using your graphing calculator, even if you don't have one, to find the maximum values. Well, we can do it algebraically. It's actually a whole lot easier. Okay? But so far, so good. All right. So I'm just going to throw an example at you. An example. I'm going to give you this function. -3 times x minus 4 squared plus 1. Do you first of all agree that that's a quadratic function? Yes, right? You just see that square is a quadratic function. If you were to open up the parentheses, you would get a, the quadratic function that equals the definition. But can we sketch a graph of that function? Yeah, no problems, right? Because we just talked about all those translations and transformations. So how we're going to do that? We're going to take a parabola, and where we're going to shift it? 4 to the right. 1, 2, 3, 4. Then what? Well, flip first, right? Remember order of operations. Do the parentheses, then multiply. So it will flip it and kind of stretch it, right? It's kind of a skinny parabola. But plus 1 is going to move it up 1, right? So I can do that. Okay? Well, do we know the vertex of that parabola? Yeah, what? For 1, right? If a parabola is expressed, if a quadratic function is expressed in that form, our job is really simple. We see the vertex just by playing with transformations. So clearly this function has a maximum value. What is the highest value this function can achieve? So you look at the y-axis, 1, right? Nothing is higher than 1 on this function. What does x have to be in order for this function to be at the maximum? 4, right? So the maximum value of the function is 1, and it occurs when x equals 4. So when our function is in this form, life is really good. Okay? So we'll call it the standard form. I don't know what you would call it. It doesn't matter. But so here's a very friendly form of a parabola. Okay? So if you can take a quadratic function and put it in this form, then automatically the vertex is at hk. Right? Agree with that? H is your horizontal shift, K is your vertical shift. Now, A doesn't really play a role in the vertex, right? All A does, it just stretches the graph of this function. The only role that A plays is determining whether we have a maximum or the minimum. If A is positive, the vertex gives you the minimum value. If A is negative, the vertex gives you the positive value. But it does not affect the location of the vertex. Is that okay? So the only thing that A tells us is whether we have a max or a min. So if A is greater than 0, then we have a minimum value. And if A is greater than 0, then we have a maximum value. So let's call this a standard form. So standard form. Nah, that's not. I'm not going to call it anything. Friendly form. Smiley face form. Makes us happy. Life is really simple. If our do you have a question? Yeah. I wrote this wrong. Yes, that should be less. Thank you. So yes, if our function is written in that form, it's really easy for us to identify the location of the vertex and therefore to state the location of the maximum and the minimum depending on the function. So again, if I give you this example, if I just draw give you this function without even sketching the graph of that function, can you state the location of the vertex? Yeah. Good. Vertex is at -1 and at -4. It goes 1 to the left, 4 down. Agree with that? Is that vertex going to give us a maximum or the minimum value? Minimum, because the coefficient in front of the square is positive. So it's a normal parabola, opens up, so we'll have a minimum. So it has a minimum value. So how's that? Does that make you happy? A little bit? Life is good right now, right? Say yes, because I'm about to start ruining it a bit. But if it's in that form, if all the variables are inside the square, then we can apply kind of all of our transformations, so we can see where the graph moves, and therefore we know the vertex, and so forth. Yeah? All right, good. Well, of course, life is not that good all the time, because I can give you this function. F of x equals, let's do something simple. X squared minus 2x plus 7, something like that. Okay? So it's not in that friendly form we can clearly see all the transformations. All we know right now is that the graph is a parabola and it opens up. That's all we know. And therefore we know it's going to have a minimum value, but we do not see where that value is. Do you agree with that? We can find the x-intercepts, but that's not what we're after. Actually, I don't think it has any. But, so we should find a way to take the function that I just wrote and make it look like one of those. All right? So we're back to looking at the problem that has a square term, just an x term, and we want to make it look like that. Right? We want to put all of our x's inside the square. So that's the third time we're about to do something very special. And we did it last time here. So what's the name of that thing I'm about to do? Complete the square. Okay, so we're about to complete the square and put our function into that friendly form. Now, the problem with completing the square here is that it's not an equation. I don't have the other side of the equation to add stuff to, like we did with solving quadratic equations, right? You find the missing term, and you add it to the both sides of the equations, and blah, blah, right? Are you with me on that? I don't have the other side of the equation here. I have a definition of a function, so I have to get a little bit creative. But it's not a big deal. So first, again, I'm just going to look at first two terms. I don't care about the plus 7 for now. It's there. I'm not going to do anything about it. So I'm looking at the first two terms. Again, when completing the square, okay, let me rewind. When completing the square, we don't like seeing anything in front of x squared. So if you don't have a coefficient in front of x squared, the life is a little bit easier. So then how do we complete the square? What do we do? That's right. So we're going to take that expression, the coefficient in front of x, so -2, we're going to, well, just, the sign doesn't even matter. Let's just take 2. The sign doesn't matter. Let's just take the number in front of x. So we will take the number in front of x, we'll divide it by 2, and we'll square it. So that's what we're adding in order to complete the square. So we're going to add 1. Okay? If this was an equation, you would have to add 1 to the other side of the equation, right? But it's not an equation. You do not have another side of the equation. So if you add 1 and you want to keep the function the same, you're going to have to subtract 1 at the same time. So I'm adding 1 and subtracting 1 at the same time, so I'm not changing the problem. But how I'm going to look at that, I'm looking at these first 3 terms as a perfect square, And then the last two constants going to give me something else. Because again, you kind of have two legal steps in all of mathematics that do not change the problem. You multiply things by 1, and you add 0. So this was an example of us adding 0. We knew we needed that 1 to complete the square. Okay? So that 1 right here is a part of this first 3 terms, which is a perfect square. But I cannot just add 1, because it changes the problem. So to keep it the same, I'm subtracting 1 at the same time. So what that gives me, the first 3 terms turn into x minus 1 squared, while negative 1 plus 7 give me plus 6. This is the same exact problem that we started with. If you open up the parentheses and combine like terms, you'll end up with x squared minus 2x plus 7.
So why did you subtract by 1 plus 7?
Because I added 1, right? Because if I add 1, that's a whole new problem now. So I want to, in order for this problem to stay the same, I have to subtract 1 at the same time. Okay, so this is kind of like adding 1 to both sides of the equation, right? If you had, you know, ax equals b, and if you add 1 to both sides, then it's okay. But what I did, instead of adding 1 to both sides, I added 1 and subtracted 1 at the same time. Because it's the same thing. If you subtract 1 to that side, you'll get that. So I know it looks silly, but I needed that 1 to complete the square. But if you add something, you have to subtract the same thing to keep the integrity of the original question. Because we don't have the other side to add 1 to. So we're piling it all on the same side. Is that okay? But after we did that, life is good. What is the vertex? Positive 1, 6, because it goes 1 to the right. And that would be the max or min? Minimum. All right, so the minimum value this function takes on is 6, and x has to be 1 in order to get there. Good? Good. Let's try another one. So let's say g of x equals x squared plus 6x minus 11. Again, it's a quadratic. We're not quite sure what the vertex is. So in order for us to find that vertex, we have to complete the square. So just like before, I will focus on the first 2 terms. I'll ignore that negative 11. I just have to figure out what I need to add to the first 2 terms to complete the square. And the way we agreed to do that, we'll take 6, we'll half it, and we'll split it. Right? Question. So what do I have to add in order to complete the square? Plus 9. But again, if I add 9, I also have to subtract 9, so I still have the same question that I started with. Okay? So this is, again, this is just adding 0 to a problem. So it doesn't change anything. So the first 3 terms are a perfect square. They factor into x plus 3 squared. Right? If you factor the first 3 terms, you'll get x plus 3 squared. While the last 2 terms, negative 9 minus 11, gives you negative 20. Okay? So you can clearly see where the shift goes. It goes 3 to the left and 20 down. So the vertex is at negative 3 and negative 20. And that's still a minimum, because the parabola opens up. Good stuff? Okay. So that's the 3rd time completing the square shows up. There'll be one more if we're lucky. If we're lucky. Okay. So does that make you happy? Of course, I'm going to come in and put a number in front of x squared to make you a little sad again, right? Because if I put a number in front of x squared, this whole thing falls apart all of a sudden. If I do this example, negative 3x squared, just to be nice, how about 12x plus 1 That is a messy function. All we know that it's a parabola and it will have a maximum because of the negative in front of x squared. But the location of that vertex is not trivial. Okay, so again, we have to complete the square in order to find that vertex. Now, remember from last week, when we complete the square and when there's a coefficient in front of x squared, what do we do with that coefficient from last week? What do we need to do about that coefficient in front of x squared? It should be written in your notes from last class. If you solve a quadratic equation by completing the square, the first, basically, second step on your list of steps said what? Right, divide both sides by that coefficient because, well, we don't like that coefficient. The problem here, we do not have both sides. I cannot divide by -3, okay? But I can factor -3. So what I can do, I can just focus on the first two terms again, just the first two terms. I don't care about that one. And I can factor out -3 out of the first two terms. So that gives me x squared plus 4x, right? I'm going to leave a little space here and then plus 1 over there. So I'm not worrying about that -3 for now. I'm just going to focus on x squared plus 4x. So what do I have to add in order to complete the square? Well, I have to take 4 divided by 2 and square it. So that's plus 4, right? But now it's very important that you subtract 4 inside those parentheses. Because look, when you do plus 4 inside the parentheses, when we do this plus 4 right here, this plus 4 is still multiplied by -3. So you didn't add 4, you really subtracted 12. Does that make sense? Because that plus 4 is still multiplied by -3, so that's -12. So if you subtract 4 on the outside here somewhere, that -4 is not, being touched by -3. So you have to do it inside the parentheses. So that -3 really multiplies both 4s. So you subtracted 12 and added 12 at the same time. That's really what just happened. Do you see that? That -3 is still there. So that's why this is harder than solving equations. And with equations, you just divide them out, and you just forget about -3. Here, it's still there, because you don't have the other side. You can't just divide your function by -3. It changes the function, right? So anyways, so the way we finish this, first 3 terms is a perfect square, right? So I can actually write it like this, -3 times, and I'm going to write x plus 2 squared minus 4 plus 1, like that. So x squared plus 4x plus 4 is the perfect square that equals to x plus 2 quantity squared. Now, if I distribute that -3, it will give me -3 times x plus 2 squared, and then plus 12 plus 1. So when you multiply -3 by -4, it turns into positive 12. So the function is -3x plus 2 squared plus 13. That's our function in that friendly form. The only thing that -3 does, it stretches the graph of the function, so it does not affect the vertex. It also flips the graph of the function. Again, it does not affect the vertex. The vertex will still be -2 and positive 13, right? That's the vertex, which is the maximum because of the negative in front. So the maximum of that function is 13. It happens when x equals -2. Yes? Do you have a question? Well, you went like that like twice. Yeah, you did. All right, good. Never mind. Is that okay? Does that make sense? This is hard. This is hard. When you start doing it, it's really hard to keep track of that extra addition. You have to remember to multiply it by the number on the outside. So this is a little bit extreme. Okay, but anyways, no? Still good? All right, good. Glad you think that. So again, so that's one way of finding the vertex of a quadratic function is by completing the square. There's another way, which is much easier, and you're probably going to use that way a lot, unless, again, you ask to put it in this friendly form. So alternative way of finding the vertex. Okay? Now, oh yeah. Well, you'll just have to memorize a little formula. Okay, so now you decide what's easier, to go through the algorithm where you don't have to memorize anything, or just memorize something and use it. So here's a thought experiment, especially for those of you who are online. What I'm about to do, I'm picking up a marker that happened to be red, but it's irrelevant to what I'm about to do. Picked up a marker, and I'm going to toss it up in the air so it does that. All right, good job, me, right? Did you pay attention to the path of that marker? What did it look like? A parabola. It looked like an upside-down parabola when, boom. All right? And I can ask you, and the way I drew it, I threw it from the ground level. So I just actually went like that. Okay. So here's a question for you. So this axis would be the time, and this axis would be a position. Let's call it S. Okay. So if I would ask you at what times during the flight of this marker, the height above the ground was 1 foot. Did that marker reach the height of 1 foot on its path? What do you think? How many times? Twice. It was 1 foot above the ground on the way up, and it was 1 foot above the ground on the way down, right? So if this was 1 foot, then we reached that height twice. Do you agree with that? Okay. And we can probably figure out the way to find that time if I give you a little more, some extra information. But let me ask you this question. How many times, or at what time during the flight of that marker did it reach the height of 20 feet? Do you remember how tall is the ceiling, by the way? 10? Really? Okay, 10, whatever. So did it reach 20 feet? No, so 20 feet is somewhere here. Let's say 20 feet. So we never reached that height. But then I can ask you, well, at what time during the flight of that marker was it at its highest point? Okay? Well, that we kind of don't know what the highest point was, but we can at least say how many times we reached that highest point. How many times? Once, right? This is that maximum. So there was some time here. There was only unique time. Let's call it t with a little m for maximum. We reached that maximum exactly once, right? So there are some heights that we can reach twice. There are some heights that we can never reach. And there are some heights, well, there's only one exact height that we reach exactly once, okay? So now if we try to connect what I'm about to say here to whatever we did last week, so we have a quadratic equation that either has two solutions, either has one solution when we reach the maximum, or no solutions, okay? And there was a really nifty trick that it was kind of happened at the end of the class, where you can predict the number of the solutions that the quadratic equation has. And that was the discriminant thing. Remember? Recall from Wednesday, the discriminant, the d equals b squared minus 4ac, that thing that's under the square root in the quadratic formula. And we agreed, if d is positive, then we have two real solutions. If d equals 0, then we have one real solution. And if D is negative, then we have no real solutions. All solutions are complex with I in it. Okay? Now, which one of those three situations will help us to find the maximum? What? D equals 0, exactly right. When D equals 0, the solution to the why am I circling that? When D equals 0, a solution to this picture would be that exactly one time we reach that height. Okay? Are you with me so far? Well, if I go back to the quadratic equation, and if D equals 0, what's left out of that quadratic equation? If D equals 0, D is that square root, right? This is D, B squared minus 4AC. If that equals 0, what is left? Negative B over 2A. So that's always going to be the location of the vertex, negative B over 2A, because that gives you only one exact solution, okay? So I can also say that the vertex of a parabola, the x value is always negative B over 2A. If you know the x value and you know the function, the y value is going to be, well, the value of the function at negative B over 2A, right? So that's always going to be the vertex of the parabola. Isn't that nice? That's really simple. Because I like that way. Yeah. Because again, it will come back again. The completing the square is one of those things that just keeps hunting you through every math course. And so there'll be another instance in this class if we're lucky, I keep saying that. But if you go further, if you take pre-calculus, it'll be all over that class. You go into calculus, it'll be all over that class. It'll just keep popping up. It's an important technique. Where was I? Okay, yes. So if I go back, negative, let me just take this problem right here. Okay? So now, in order to find the vertex of this, I'll just have to go, right, negative b, so it's negative of negative 12 over 2a, 2 times negative 3, right? Negative b over 2a. Do you agree with that? Which is positive 12 over negative 6, which is negative 2. Right? Wasn't that the x location of our vertex when we did it by completing the square? Yeah, you see we have negative 2. So we found the x value. To find the y value, we'll just evaluate our function at negative 2. So that's negative 3 times negative 2 squared minus 12 times negative 2 plus 1. Right? And that will probably come out to equal 13. But if I do the computations, it's negative 3 times 4 plus 24 plus 1. So that's negative 12 plus 25. So that's 13. So the vertex is negative 2 and 13. Okay? So the way you remember that, the vertex is whatever your quadratic formula without the square root. Negative b over 2a. Okay? Actually, it's really easy to remember. If you know your quadratic formula, just remember that we obtain the height of a maximum or minimum exactly once. So discriminant equals 0 and all that good stuff. Is that okay? Now this means no matter how ugly the problem is, we can now always find the vertex by doing this little trick. If I give you something ugly, like that, g of x equals 1/3 x squared minus, what would be a good number? Okay, 2x plus 2/3, something like that. To do this problem by completing the square, we can, it's just a little messier because we have fractions. But we can find the vertex now with a relative ease. We can just say, well, x equals negative b, so it's negative of negative 2 over 2a, right? So that's positive 2, so it's 2 divided by 2/3. Do you agree with that? So it's the same thing as 2 times 3/2, so that's 3. Is that okay? So that's the x value, x location, x coordinate of the vertex. The y value, just plug it into your function. So g of 3, so that's 1/3 times 3 squared minus 2 times 3 plus 2/3. Right? Just you plug that value into your function, so that's 1/3 times 9 minus 6 plus 2/3. What is 1/3 times 9? 3 minus 6 plus 2/3. So that's negative 6 plus 2/3. I'm sorry, negative 3 plus 2/3. And what is negative 3 plus 2/3? Negative 2 and 1/3, right? Whatever that is. So that's the vertex. 3, negative 2, and 1/3. Okay? Any questions on that? Make sense? Good. Do you remember we did that problem when we were fencing off a thingy for cows along the river? I'll tell you the joke you didn't get. Remember that? There was a river, and it was something like this, wasn't it? Like that. 3 rectangles, and we call that x, 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 x. And the total amount of fencing was, I don't remember the number, make one up. I think it was like 3,200. Let it be 3,200. So 3,200 total feet of fencing. So find the value of x so we have the maximum, right? The maximum area enclosed. So we were working through the problem to find the area. We just said, okay, well, let this side be y. And we said, all right, well, the area equals x times y, right? And we want to maximize that area. Now, the problem, we have 2 variables, x and y, so there should be a way to express y in terms of x, and we knew that we have x, 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 x. So we knew that 4x plus 1y equals 3,200, right? I'm not saying this is the exact same question. It's close, and I think I don't know if we had 3 areas when we just had 2 areas, but doesn't matter, same problem. So therefore, y equals 3,200 minus 4x. So I can take that and plug it in here. So area now is a function of x equals x times 3,200 minus 4x, right? So a of x equals, if I distribute the x, it is negative 4x squared plus 3,200x. Good? So this is the function that gives me the area as a function of x. We recognize this as a quadratic. Do you agree with that? It's a quadratic function. The coefficient is negative, therefore it's upside down parabola, produces the maximum. Now before, in order to find that maximum, you have to plug it in your calculator and then start messing with it. Now, all I have to do is to find the vertex of this parabola, okay? And that will give you the maximum value. So all I have to do is to find the vertex. So x is negative b over 2a, so it's negative 3200 over 2a, and a is negative 4. So this is 3200 over 8. That should work pretty, right? What is that? Isn't that 40? Yeah? 40? Oh, 400. 400. Yeah, so 400. So right away, x has to be 400 in order to maximize the total area. Okay? Now, what is the total area? What is the maximum possible area? Well, we have to plug it into our function. A of 400 would equal to negative 4 times 400 squared plus 3200 times 400, right? That will give me the maximum possible area. So whatever that is, something with 64. I'm not sure how many zeros. 64, 4 zeros. If we plug it in our calculator, where's my calculator? 3200 times 400, 128, 4 zeros. Minus, okay, I'm not sure whether this thing is smart enough. Negative 4 times 400 squared, right? Okay, let me try it again. I hate calculators, they're awful. Squared times negative 4 is that, plus before we got 28 4 zeros, so yes, 64. Good. Good job. All right. Wasn't that joyful? We just solved that problem without doing the graphs. We can find that. No, because the box one will be a cubic. Okay. Where didn't you get it? Yeah. Well, we'll talk after class. Didn't I did a box in class. Well, it's recorded. Go back and look at it. This is why I'm recording it. If you don't remember it, look at it again. It's all there. But I won't be able to do the box with that because it's a cubic function. We don't know how to find those points on the cubic. Okay. But I wanted to do something about that marker again. So I believe on planet Earth, the height of a free falling object at time t in seconds is given by the formula S of t equals negative 16t squared. I'm going to write it down, and I'm going to tell you what each of those funky letters mean, plus v sub 0 t plus S of 0. Now this is in feet, so the height measured in feet, where v0 is the initial velocity and S0 is the initial position or initial height. Which are usually given to you, okay? So if I go back to this little marker problem, the one that I just threw, let's be more realistic. So I went from about this height, right? I went like that. So how far above the ground? About, what, 3 feet or so? Okay, so we threw a marker from 3 feet above the ground. Okay? Now, do you remember how hard I threw it? What do you think the initial velocity of that marker was? How fast was it going? Just guesstimate. It doesn't have to be precise. What do you think? How fast was it going in feet per second, please? You want me to repeat that?
15 feet per second.
All right. Whoa. I threw it hard. All right. Anyways, with the initial velocity, that's okay. I had help. All 15 feet per second. That doesn't matter. Okay? All right. So therefore, right away, the height at time t is this. S of t equals negative 16t squared plus 15t plus 3. So 15 is my initial velocity, 3 is my initial height. You do not have to memorize this formula if you know. Just know that it's there, know where to find it on your homework, on the exams that will be given to you if you decide to put a question like that. Okay? You don't need to remember this is from physics. This is the formula of a free-falling object on planet Earth. Okay? Other planets is different because of the gravity. All right. Okay, so good. So we got that. That's our function. So let's do a little break, and then we'll do more with that, right? It's time to take a little break. And then we'll work with that function. We'll try to answer a few questions. So let me pause this. Okay. So we found that function. Now let's play with that function. So this function gives me the height of the flight of that marker at time t. So I can ask you a whole bunch of questions like, tell me the height, find the height after 2 seconds. So I want to know how high is that marker above the ground 2 seconds after I tossed it, right? So all you have to do is to evaluate S of 2. Okay, so they'll tell me precisely how high that marker was at 2 seconds if it might not work, actually. 2 seconds might be too long of a time. It might have landed after 2 seconds. But what do we get? We get negative 16 times 4 plus 30 plus 3. So negative 64 plus 33. So that looks kind of negative, right? So what does that tell you? It definitely landed and it went through the ground and it kept going in. So 2 seconds might have been too big of a stretch. But that's how you would do it for any given time. Okay? So already landed. I can ask you this question. When will the marker reach the height of, let's say, 5 feet? Okay, so I'm giving you the height, and I'm asking you when will that happen. So you have to solve this equation. S of t equals 5. So for us, it is negative 16t squared plus 15t plus 3 equals 5. Can we solve that equation? That's a quadratic equation, right? So subtract 5 from both sides, so it's negative 16t squared plus 15t minus 2 equals 0. So probably, most likely, it's not going to factor. So how will we proceed if we cannot factor? What? Yeah, quadratic formula. Another thing that you can do, if you start with a negative, it's a little awkward to solve quadratic equations when they start with a negative. You can multiply both sides by negative 1. It'll make your life a little bit easier. If you change all the signs like that. So if I plug it in the quadratic formula, so t equals negative b plus or minus the square root of b squared minus 4 times a times c all over 2a, right? Quadratic formula. So t equals 15 plus or minus the square root of 225, 15 squared, minus what? 128 over 32. Is that right? So it's 15 plus or minus the square root 125 minus 225 minus 128. Is it 97 over 32? 97. Is that a prime? Yeah, I'm not sure. It's always hard to tell whether a number is a prime. Do you know that? That's why the internet security almost works, because it's hard to tell whether a number is a prime. That's what they use. They use very, very large prime numbers. Well, what is it? If I plug it in a calculator, 97 square root of that, so whatever that is. So we'll get two answers. 15 minus square root of 97 over 32. So that's one answer. So what is it, 0.16 of a second? And the other answer, if I do 15 plus square root of 97 over 32, so about 0.78 of a second. So the height of 5 feet was reached twice. On the way up, 0.16 of a second, and on the way down, 0.78 seconds after we launched the marker. Okay? Does that make sense? Just solving quadratic equations, giving the formula, setting it equal to whatever the height we're getting at. And finally, I can ask you this question. Find the maximum height reached by the marker. So again, our function was negative 16t squared plus 15t plus 3, right? So all I have to do is to find the vertex. Now it's going to be a little ugly. So the vertex, x equals negative b over 2a, so it's negative 15 over 2 times a. So negatives cancel, so it's 15 over 32 seconds, whatever that is. Okay, so it's a little bit less than half a second after I threw that marker. That's when it got to the highest point. Now, in order to find that height, so the maximum height, what do I have to do? If I know the time, I want to know the exact height at that time. What? Yeah, plug it into my function. as of 15 32nds. So whatever that is. So that equals to negative 16 15 32nds squared plus 15 times 15 32nds plus 3. Whatever that is, it's a number. I can plug it in my calculator, right? Or I can work it through. I'll just plug it in my calculator. 15 32nd, boom. Square that times negative 16 gives me that much. I'm going to put it in my little memory. Then I'll go 15 over 32nd times 15 again, gives me that much. I'm going to put that into my memory, and then I have a 3, I'll put that into my memory. Okay, now how do I get things out of my memory? MR? Yeah. So that's the height. 6.5 feet. So approximately 6.5 feet, a little bit above that. Isn't that fun that we can answer those questions? That's kind of a big breakthrough in our abilities. Don't you think? We'll never be able to answer those questions before. Just threw a marker, made an experiment, came up with function, found everything really I need to know about the path of that marker. Whatever you want to ask yourself, we can answer now. How long it takes to get to this height, how long it takes to get to that height, what is the maximum height, how long it takes to hit the ground. I can figure that one out. How long does it take to hit the ground? How would you answer that question? So you started with 3 feet above the ground, you tossed the marker, it landed somewhere down there. How would we solve that? How would we find the time it took that marker to get to the ground? What is the height of the marker on the ground? 0. So basically we have to solve this equation. The position is 0 when it's on the ground. So it's negative 16t squared plus 15t plus 3 equals 0. That's easy to solve. It's a quadratic equation. You'll get 2 answers, one positive, one negative. The reason for that, because I started from 3 feet above the ground already. Because it will give you 2 solutions. One at 0 on both ends. One of those ends will have a negative, kind of almost going backwards in time, kind of weird. So we're going to choose the positive one. So that's how long it will take. I'm not going to solve this, just plug in the quadratic form. Does that make sense? Funky stuff. Yeah? All right. And if it doesn't, you can watch it again. All right. What? This is why I'm doing this. You know how much time I'm spending on posting all this crap on YouTube and the angry letters from YouTube that I get for posting 2-hour videos on it. They don't like that stuff. It's 2-hour video. You know, I'm not getting million views per video. It's just like 2 every time. So they're really upset about that. Because, you know, it's 2-hour videos. Nobody's watching. So take advantage of that. Okay? So 3.4. Thank you. You're welcome. Thank you for what? Oh, okay. Good. So 3.4 is dealing, we're actually going to be on 3.4. What? What about the quiz?
Just said no, we have one this evening.
When's the test?
It's on the syllabus.
No, Monday.
Yeah. It's like October 3rd or something like that. All right, so that's dealing with radical and rational equations. And the section 3.4 on your homework is split in two parts. First homework for this week only covers half of section 3.4, and the second homework for this week will pick it up from section 3.4. So you have, two homeworks, 3.3, half of 3.4, and then half of 3.4 and 3.5. And then the quiz, and then we'll review it, and we'll take the test. So we'll just talk about equations that involve radicals, okay? So let me ask you this question. Here's an equation that involves radicals. Square root of x equals 2. Can we solve that equation? How would you go about solving that equation? Square both sides. Why did you decide to square both sides? Get rid of the radical. So that looks very reasonable to me. You want to do something to one side of the equation, we'll do the same thing to the other side of the equation to get rid of the radical. So x equals 4. Everybody happy with that? So we proceeded by the means of, well, killing the radical. Is that okay? Square root, so square both sides. What if we had a cube root? Cube root of x equals 2. How would you go about that? That looks reasonable again, because if you take a cube root and you cube it, you'll get x equals 8. Okay? Very reasonable, right? Now, the problem with that is you really have to check your answers. When you solve equations that involve radicals, you kind of must check your solutions, because some of them you can do everything correct. All your steps are perfect, the algebra is good, and you got the answer, and that answer doesn't work. And you haven't made no mistakes. Everything is correct, but it might still produce an answer that doesn't work. And let me show you this example. Don't write this down. But I'm going to give you the easiest equation of this whole semester. Ever. The easiest equation in existence. Okay, here's an equation. Can you tell me the solution to that equation? 1. Is that right? I mean, that's the only x that solves that equation. Are there any other solutions that solve this equation? Are there any other numbers that make this work? No, only 1. Do you all agree with that? Everybody's happy? Okay. Now let's see what happens if I square both sides. If I square both sides, I'll get this equation, x squared equals 1. Well, let's solve that equation. What are the solutions to that equation? 1 and negative 1. All of a sudden, we got an extra solution that wasn't a part of the original equation. So solutions like that, when you're squaring both sides, sometimes we get this extra solution that does not satisfy the original equation. We call this extraneous solution. Okay? Because when you square both sides, you just start ignoring things that are negative. Okay, so extra thing pops up. So when solving equations that involve radicals, because sometimes you have to square both sides, you really have to go back and check your solutions for those extraneous ones, because you're not making any mistakes. It's just extra solutions show up. I'm not saying it's going to happen every time, but it just might. And this is the simplest example that showed if you take an equation that only has one solution and you square both sides, all of a sudden you get two solutions. One of them does not work in the original equation. Okay? So here are the steps to solve equations that involve radicals. So step 1 would be to isolate a radical. Okay, you want to get a square root or a cube root or whatever root you have separated on one side of the equation. Okay, so first step is to isolate Isolate radical. Doesn't, I don't know, the radical, irradical. So meaning, get radical by itself. Second step would be to kill that radical. Okay? And we kill the radical by, either squaring or cubing or whatever. Okay, so raise both sides. Of an equation to the index of the radical. Which means if you have a square root, square both sides. If you have a cube root, cube both sides. If you have a fifth root, raise both sides to the power 5. Okay? Now, after you did that, there might still be another radical left. Okay, so check for more radicals. Because you might have started with 2 square roots. You cannot kill both at the same time. You kill one at a time. So check for more radicals. So if there are radicals left, if there are any radicals left, repeat steps 1 through 3. So you go back, you isolate and kill. If there are no radicals left, move to step 4. So the first part of this game is to isolate and kill, isolate and kill, isolate and kill, till you have no radicals left. And after you do all that, you're just going to end up with some kind of a polynomial-friendly equation. Okay, so no radicals left, so step 4 would be to solve the equation. And step 5, which is very important, check your solutions. Your solution for extraneous roots. But isolate and kill, isolate and kill, isolate and kill. That's what we do. Good? Yeah. All right, let's try an example. So something simple, square root of 2x minus 1 equals 3. Okay? So here's an equation that involves a radical. So all we have is a radical on one side of the equation. The step 1 tells me to isolate a radical. Well, it's isolate, right? One side of the equation is nothing but a square root. So I'm going to go ahead and kill that square root. And how do I kill a square root? Yeah, so I'm just going to go ahead and square both sides of that equation. So therefore, on the left, I have 2x minus 1. On the right, I have 9. Okay? No more radicals left. I'm going to go ahead and solve this little equation, which is very nice, right? So now proceed solving this equation. Add 1 to both sides. 2x equals 10. Right? Divide both sides by 2. X equals 5. I have to check. All right? I really do. And there are patterns, there are ways to predict whether you're going to have extraneous or not. But safe thing is to check every time. So to check, that means I'm going to take that solution and plug it into the original equation. So I want to see whether 2 times 5 minus 1 under the square root, will that work with that equation? Will that equal 3? And it looks like it does, right? We'll have a square root of 10 minus 1. Will that equal 3? So that's a square root of 9. That does equal 3. So that works, right? So we have x equals 5 is a solution. Is that good? All right. Let's try one more. I have to be really careful. How about this? The square root of x plus 1 minus 2x equals let's just do 1 equals 1. Okay? So square root of x plus 1 minus 2x equals 1. So there's an equation that involves a radical. So what is the step 1? Yeah, get the radical by itself. So it means add 2x to both sides, right? Get rid of that 2x. So add 2x to both sides of the equation. Get the radical by itself. So we have a square root of x plus 1 equals 2x plus 1. So now radical is isolated. So we're going to square both sides to kill it. So that's the step 2. Square both sides to kill that radical. So the left-hand side is just x plus 1. Right? Just kills the square root. While the right-hand side is 4x squared plus 4x plus 1. You can either FOIL 2x plus 1, 2x plus 1, or you can use the formula that tells you how to square a sum. But we got to this point. Are there any radicals left? Are there any more radicals? No. So I can go ahead and solve that equation. How would you go about solving that equation? Yeah, make it equal to 0, so subtract x from both sides. Subtract 1 from both sides. We'll get 4x squared plus 3x equal 0. Right? Well, how would you solve that equation? What? Well, I can, but it will be an overkill. I can factor that, right? Yeah, I can take out an x, but I can do it by completing the square. It'll just be a lot of extra work. So it's either x equals 0 or 4x plus 3 equals 0. So x equals 0, x equals negative 3/4, right? You subtract 3, you divide by 4, okay? So we got two potential solutions. We haven't made any algebraic errors yet, but I still have to check them. And I don't know whether both of them might work. I don't know. So I'm going to check. So my problem was that original square root of x plus 1 equals, no, square root of x plus 1 minus 2x equals 1. So let's check 0 first. So x equals 0. So if I plug in 0 into my equation, which is the square root of x plus 1 minus 2x equals 1. Does that work? We just get square root of 1 minus 0, really. So yeah, square root of 1 equals 1, so check. So x equals 0 works. Okay? Let's try another one. X equals negative 3/4. So if I plug that into my equation, so square root of negative 3/4 plus 1 minus 2 times negative 3/4, will that equal to 1? That's what I'm checking. I'm plugging every solution that I'm getting back into the original equation. So the first is the square root of 1/4. And the second one, it's positive 2 and 4 reduces 3 halves. Well, that equals 1. I mean, 3 halves is already bigger than 1, right? And you're adding something to it. So it's not going to equal 1, right? Actually, it will equal 2. You have 1 half plus 3 halves. That's in no way equal 1, right? So that's an extraneous solution. So this thing right here is the extraneous. The only solution, x equals 0. And again, there is no way to predict. That doesn't just mean every negative solution is extraneous or every fraction is extraneous. It's just, both of them could have worked, by the way. Just in this case, one didn't work. Okay? So this is why you really have to go back, substitute, and check. Okay? There's no way to predict without checking. So is that okay? But again, the steps are isolate and kill, isolate and kill. Let's try this one. I have a square root of x plus, and I have another square root of 2x plus 1, like that. So I have kind of a double radical. That happens sometimes. Equals, I don't know, it's not going to come out pretty. Yeah, it just, I don't know, 4. It'll come out ugly, sorry. But anyways, what we see is that on the left side is one gigantic square root. And that's all I see. I don't care what's underneath it. All I see is the square root equals 4. So I'm going to go ahead and kill that square root. And we'll kill the square root by squaring both sides. I'm going to square the left side, and I'm going to square the right side. So all I just did, I killed the most outer square root, the biggest square root. So I'm left with whatever is under the square root, which is x plus the square root of 2x plus 1 equals 16. Right? See that? So we killed one square root. We're left with what's under that square root. No matter what it is, that's what we have left. Okay? So we did step 1 to step 3 says check for more radicals. Do we have more radicals left? Yes. So we're going back to step 1, isolate the radical. So subtract x from both sides. I want to get the radical by itself. So the square root of 2x plus 1 equals 16 minus x. Oof, big numbers. Okay? Now again, radical is isolated, so go ahead and kill it. So I'm going to square both sides. So that gives me 2x plus 1 equals 16 squared, 256, is that right? Minus 32x plus x squared. So again, you either FOIL or you do the formula with a double product in the middle. So now there are no more radicals left. This is a quadratic equation on the uglier side of quadratic equations. Again, the numbers came out huge. But get everything to one side, so subtract 2x, subtract 2x, subtract 1, subtract 1. So we'll end up with x squared minus 34x plus 255. Oh boy. Is that right? Equals 0. Is that right? Well, looks right, right? Yeah, well, now we have to solve that quadratic. Now that's, I don't think you can factor that, because 255 is 51 times 5, right? And 51, that's a prime. So you cannot factor that. So if we cannot factor something, we're going to use the quadratic formula. So negative b, so negative of negative 34 plus or minus the square root of negative 34 squared minus 4 times a, which is 1, times c, 255, all over 2a, 2 times 1. So we get 34 plus or minus the square root. What is 34 squared? 1156 minus what is it? 1020? 1020? No, wait, yes. 1020. If you multiply 4 by 255, am I correct on that? Yeah. So that leaves us with 34 plus or minus the square root of 136 over 2. Okay. Now, 136 is not a perfect square, but we can simplify that, right? 136 is definitely divisible by 4. 136 equals 4 times 34? Yes. So if I do that, so it's 34 plus or minus the square root of 4 times 34 over 2. I can take the square root of 4, which is 2. So we get 34 plus or minus 2 square roots of 17 over 2. Right? Divide both by 2. 17 plus or minus square root of 17. Oh, that's a funky looking answer, isn't it? Yeah? So there are 2 of them. You have 2 solutions. Checking them is going to be a pain. Okay? Because they're ugly. But, so let's try. I mean, I have to try. I have to take those answers and plug them into my original expression. And I'm going to have to use a calculator here, that's for sure. Okay? I'm just going to plug it in, on a calculator. Now, if you have a graphing calculator, it actually might be a little easier. But if you don't, on a regular scientific calculator, let's do one of them. 17 plus square root of 17. So that's that, right? So I need to multiply it by 2. So I'm going from the inside. So I'm doing the 2x plus 1. So times 2 gives me that. Plus 1 gives me that. So I computed 2x plus 1. Okay? Then it says take the square root, so I'm going to take the square root. So give me that. Okay? Now I have to add x to it again, so it's plus 17 plus the square root of 17. So it gives me that. Now if I take the square root of that, that does not equal 4. Right? I wanted 4. So did it work? No. So that didn't work. Let's try the 17 minus the square root of 17. So it gives me that. Times 2, so times 2, plus 1, plus 1, square root. That looks familiar. Did I do minus and the plus in the previous one? Yeah, I think I'm making a mistake. Let me try this again. Maybe both of them don't work. That can happen too. Yeah, that looks good. That was the first one, didn't work. When I do the second one, 17 minus that times 2 plus 1 square root of that, and then plus 17 minus yeah, that doesn't work either. Both extraneous. Isn't that lovely? Okay. No solution. All this hard work. Almost makes me a little sad. Did we make a mistake? Is 16 squared 256?
Pretty sure.
I'm pretty sure too, but now I'm, yeah. 6 and 4. Oh well. Just didn't work. Let's try another one. Makes me sad. How about square root of x minus square root of x plus 1 equals 2? Let me think for a second. Yeah, that's not going to work. Let's make it plus. Maybe it'll work. Let's make it a plus. Okay. What is step 1? What's step 1? Isolate. Is it isolated? No, I have 2 radicals on one side. I only want to have 1. What? No, because then I have to square. It'll give me a whole harder, bigger radical. Right? Because when you square, you're really going to FOIL that. So it gives me a nasty radical. So you still have to isolate. So subtract. Well, let's just subtract the square root of x from both sides. It might be a little easier if we subtract that. So that gives me square root of x plus 1 equals 2 minus the square root of x. So I have one of the radicals is isolated, so I'm going to square both sides. Square, square. So the left-hand side is x plus 1, while the right-hand side, and this is why we have to isolate, you have to square the first, which is 4, but then you have to subtract their double product. So they're multiplied together times 2, so that's 4 square roots of x plus x. Yeah. Okay. So I still definitely have some radicals left, don't I? So let's see. So I need to isolate this thing right here. I need to isolate this radical. So first, subtract x from both sides. So they just cancel, right? And then you can subtract 4 from both sides. So you have negative 3 equals negative 4 times square root of x. Right? Is that okay? So divide both sides by negative 4. You have square root of x equals 3/4. Well, that's a nice little equation. So to solve that, we're going to square both sides. we get x equals 9/16. Okay? Are we done? What do we need to do? What? Check it, right? Because we get the only solution that we got might not work. So I have to take 9/16 and I have to check it by plugging it into the original. So I have a square root of 9/16 plus the square root of 9/16 plus 1. Will that equal 2? So let's see. The square root of 9/16 is 3/4 plus the square root of 9/16. 9/16 plus 1. We're going to turn 1 into 16/16. So this is 25/16. Will that equal 2? Are you okay with that? How we got 25/16? I just added 1. Yeah, so this is 3/4 plus 5/4, which is 8/4, right? Which does equal 2, so that checks out. So we got the only solution, and it checked out, and it works. Why not? No. Right? One is 3 squared, the other one is 4 squared, so they don't have common factors. But yes, if you could reduce, if this was like 9/18, then yes, reduce it to 1/2. Okay, but again, review that. I mean, that previous example was a whole, it was ugly. Still surprised. Makes me unhappy. Did I make a mistake? There gotta be an error somewhere. Did I? All right, I'll review that. Maybe I'll find something. But anyway, so the steps, isolate and kill. That's the first thing. And really, because if you have two radicals on one side, you really have to make sure you're just nothing but a radical. Because if you're squaring a radical plus something else, the radical doesn't go away. You're going to end up with a new radical because of the way the formula works. So isolate and kill. And when you don't have any radicals left, solve whatever equation you have and always check your solutions because you might get extraneous ones. Is that okay? Any questions? Oh, good. Then I'm going to stop. See.